Wonderful. Thanks, Joe. So welcome, everyone. Thanks for joining us this afternoon. I was telling Joe just a few minutes ago, doing a webinar on a Monday is unusual. I usually schedule my webinars on Friday afternoons. Unfortunately, we're running into schedule conflicts, and we're running close to the end of June, and then leading into summer vacations. Especially if you're in Eastern Canada, then summer is short and hasn't really started here, but it's still very short when it comes. So we want to take advantage, and I'm sure northeastern U.S. is probably in the same situation. So we all want to take advantage. My name is Joelle Guénette, and I'm the territory manager for Eastern Canada, so Ontario to the Maritimes. And I have with me Joe Galliera, who will be hosting this. Michel Cloutier, unfortunately, couldn't join us today, but he's normally on with us to handle the logistics of things. And for most topics, he's often the one giving these. So we'll catch him on another one. So once again, thanks for joining us. Just over a week ago, on the 7th of the month, Joe hosted a call, which was an introduction to simulation done by computational fluid dynamics, so better known or easier said as CFD. And hopefully you joined us for that first session, which was the beginning of the call, the introduction on our simulation solutions from SOLIDWORKS for that particular aspect of simulation. Giving people the option of not doing things always through physical prototypes, but being able to simulate digitally within your SOLIDWORKS environment with your SOLIDWORKS model, so that you can have a better idea of what works, what doesn't, letting you be more innovative and giving you more confidence into the quality of your product. Today's topic is expanding on that. We're going to go into some very specific modules that we add on to our simulation flow solution product. And these are for very specific applications, obviously, and Joe's going to take us through that. So if you were here last time, you heard a little bit about Joe's background. If you are not, I will take a minute to go back through. So Joe comes from simulation. This is what he does, and more specifically, CFD. So we internally call him Flow Joe because that is what he does. That is what he is. So his knowledge of this product, what you can do, what you can't do, because obviously everyone wants to do everything and anything with software, but sometimes the software needs to catch up to people's wishes, and that's what we try and do every year with our new releases. But Joe's been working in this field for a long time, mostly in aerospace world with NASA and with Paul Aerospace. And he's been with SOLIDWORKS for over 16 years now, dedicated to simulation and very focused on the SimFlow solutions. So we're happy to have him here with us today to take you through this information. And as he said, if you've got questions, please put them in the chat area. And if time permits at the end, we'll come back and address them. And otherwise, we have notes of who put them in there, so we'll be able to reach back out to you and get you some more info. And I will come back at the end to wrap this up, but in the meantime, I'll hand it over to you, to Joe, to take this away for us.
All right, Joelle, thank you very much. All right, yeah, so those questions, last time we ran out of time. It may be the same case today. But I did respond to everybody's questions directly by email. So today we're focusing on HVAC and electronics cooling, and you might ask yourself, what exactly do we mean in that regard? So flow simulation sort of differs from the other simulation products, and I cover all of the simulation. We have our FEA solution, SOLIDWORKS simulation, we have plastics, and we have flow. So those first two, the FEA and the plastic injection molding simulation, they come in 3 flavors like we typically do: standard, professional, and premium. Flow simulation is the odd one out here in a way, just because of the nature of how it is, that you're solving these flow equations in heat, and they're very much a part of one another. So we offer just a standard package for doing most of the calculations that would be needed for doing internal and external flow and heat transfer, and you can see the whole list of things here. Now, what we're specifically talking about today are two add-on modules to that flow simulation. So to be clear, you have SOLIDWORKS as your design tool, and then you can add simulation, flow simulation specifically here, as a tool to use for flow and thermal simulation capabilities. And then on top of flow simulation, we have two add-ons, electronics cooling and HVAC. And I'm going to go into details in regards to these two in a little bit more. But just briefly, they really help you to streamline, if you're in these either one of these industries, really helps you to streamline the process into solving problems, and it has capabilities that are outside of the standard tools, such as doing joule or ohmic heating is one example here in the top left for electronic cooling that you can't do otherwise. And then with that, you can apply a current, DC current or voltage potential, and it'll calculate what the thermal heat up the temperatures due to the resistance in the material that is conducting the current there. Yeah, so I'm just going to go, you can look at this, and we'll come back to it possibly later on when we took a look at it, but that's the focus for today. So just to recap, last webinar, we did show two separate types of analysis: an external airflow calculation, and there I was focusing on calculating pressure drops and drags, and also on meshing of a very complex detailed model of a human running down the field. And then we did an internal water flow problem through a valve, this globe valve, and we were able to use our goals to calculate the CV value. So, these are two different ways that you can use flow simulation, external as well as internal flow. And in that webinar, there's certain things that we covered that I'm not going to have time to cover today, but basically how to set up a new study, using a wizard to start from scratch or setting up a new problem from a template, using goals that can be used to monitor the calculations of certain specific things you're interested in, finishing the calculation when it converges, or calculate certain things like CV or pressure drop, drag coefficient, and things like that. I showed you how to do some automatic meshing as well as manual meshing techniques that we have for global as well as local areas, as well as doing adaptive refinement. Result plots, I showed a few of these types: cut plots, surface plots, trajectories, and doing charts in Excel does it very well. And you'll see a little bit more of that today, actually, because you can't get away from results when you're doing a presentation like this. And it's very visually enticing as well, so we'll have a lot of nice visuals for that. And then we have multiple study types that I introduced: cloning, parametric studies, and running as a batch run. All right, so you can review that webinar. I put the link to the Eastern Canada webinar launch page, so you can review that if you wanted to. So here's the URL. You can capture your VR code on the on there by your camera if you wanted to. All right, so we're going to first jump into the HVAC module, right? And the first example I'm going to use is going to show you how you can calculate ASHRAE comfort parameters and use advanced radiation within this. So let's jump into this example, and I'll talk to it a little bit more here. All right, so in this example, I have, let's play these flow trajectories here. So what we have is, this is a room where we have a dummy person here that's working on a computer screen, and just through some of these heat sources, I can display the call out. So you have nice flags that you can show. So the person here is generating 30 watts of heat, and the computer monitor, say the computer is generating 10 watts of heat. So that you can see air rising, and actually I can change the temperature profile to get some hotter temperatures coming off of the body here. So you can see those listed like that. Let me hide these call outs. And this is just a typical setup that you would have when it may be at night or after the sun has gone down. And so it's a cool room. It's not really getting much above, say 20 degrees C, 22 perhaps. But you can get an idea what's the situation here, all right? A little bit more of the setup is that we just have a inlet flow volume. So we know that there's inlet flow of 200 CFM coming here. Temperatures coming in at 15 degrees Celsius, I guess is kind of cold. And we can set those parameters here, thermodynamic parameters at 15 degrees C in our setting there. All right, so this person likes the room pretty cool. So we're just showing that as an example of that. Now, the situation changes when we have solar radiation, all right? And if we show these same plots for solar radiation, you can see that, and also I can include here, show the solar radiation is coming in at an angle during a certain part of the day, and I'll show you how we can set that up. And you can see the result of that. Sun is coming through the windows from the outside and heating up this, shelf or area there, and even the person on this side is getting a little bit of that heat there. All right, so this is with solar radiation. Now, because this is such and in such a way that you have that really powerful solar heat, and you may be familiar with that when you're sitting in a car or other things, the solar radiation can really heat things up. So one of the things that we can use as parameters to determine whether it's a good environment or not, there's two ways, and I'll just show these at first. Let me do this cut plot, the predefined one here I set up. I guess was not in a good location, but we can select here from our contours this percent people dissatisfied, PPD. All right, so you can see it goes from 0 to 100%. And if I move this along here to where the person is at, you can see it's, it's relatively low, so it's a pretty good environment. Let me change this to have it on this plane here, and I can show a preview of this. So now you can see some more coloration here where there's areas that, whether it's really cold or really warm, areas in which, a person would not be satisfied in those certain situations. So these are specific parameters that you can calculate with the HVAC module, and it's a setting that you can define in your calculation control options when you set up your solving options to click on here to calculate your comfort parameters. Now, again, that is only available with the HVAC module, all right? And the solar radiation is something that I hadn't mentioned before, but with a heat transfer that you can do in flow simulation, you can do all types of heat transfer, whether it be conduction, convection, and radiation, whether solar or environmental radiation, and you can do body-to-body radiation as well. If something is like heating up, like a electric heater inside an oven, right? I have a simulation that I've demonstrated that that can heat up the oven inside through just radiation, as well as conduction and convection to the air surrounding it. Okay, so how do we set that up? Well, in our general settings, we have some options. So this is typically when you're setting up a new problem through the wizard and you're setting up your physical settings that you want to include. You can add heat conduction in the solid. It's always done within the fluid as well, right? And then you can add different radiation models. So one is called discrete transfer and the other one's called discrete ordinate. And I'll describe these a little bit better. But for this option, because we have glass involved in this environment, I'm using this discrete ordinate method. And we've included radiation. And you can define radiation in a couple different ways. In this one, I chose to do it a location and time. So Boston, Massachusetts, so choose the latitude by defining the city. You can see a whole list of cities here. And you can even define your specific latitude for that. If it's not already defined, you can do that in the library. You can set the date, the time, even the cloudiness for the solar radiation, and it utilizes a database of information and setting that up properly. Or you can set it as direction and intensity, or azimuth and altitude are different ways you can define that. And then in SOLIDWORKS, there's a sunlight model that you can define and even do it throughout a day. And if you would want to do it as a transient analysis, you can also model that and pull that in directly from that model as you had set it up in the SOLIDWORKS model. Now, with the discrete ordinate method, we have the ability to do absorption into solids. And so that's one of the specific things I'm going to highlight in this. And we can define certain bands. So this is all going to be described. And then, of course, when we're doing heat transfer, we want to include convection, and it's driven by buoyancy of the air as it is at different temperatures. So we always define gravity. So that's the basic setup for this problem. And you can see how percent people dissatisfied is set up here. Another parameter is predicted mean vote. And I'll show this, and it's on the scale between, and let me just set some options here so you can see it a little bit better. I like to, I'll make this 500. So increase it a little bit more here and set the number of colors. So these are things I didn't show before that you can do with the results. It's very interactive in a manner that you can define here. So it's set from a scale from -3 to +3, and then 0 is the Goldilocks in the middle. So you have, as I call it, typically the Goldilocks values, right? So too cold, too hot, or just right. So predicted mean vote is set up like that. So those are two different ways that you can define as ASHRAE parameters when you can set up. And even I will mention that the person that's here doing work, if you have it in a factory and people are working or something like that, you can actually define the amount of clothing that somebody has on and the amount of activity that they're doing. So those can all play into how those parameters are going to affect the people that are in that environment. All right. And then I'm going to do one, this other project, the final one I'm going to show for this one is, and you can see by the descriptive name that I put in here, with solar radiation shielding. So the glass, we can add some shielding onto that by defining that with a quartz material that will absorb the energy of the sun, right? So when we're defining the material properties for the glass, I guess it's both on the outside and then there's some glass windows here for the interior of their office, we can set this parameter and it sets it up as an absorptive type of flow. Now that's only again available with that discrete ordinate method, which is part of the advanced radiation module within the HVAC. All right. So a little bit more information into this. In our material library, you can see here the absorption coefficient for radiation can be set through a table. And this is basically typical of glass material, and I'll show it in a little bit more, that it has certain bands of absorption that it does it at different wavelengths. So different wavelengths and the amount of absorption coefficient is defined like that. So when I set up the absorptive radiation transparency, we have those 3 bands, and then it can calculate what the average values are in the wavelengths less than 175, between 175 and 2700, and then above 2700 nanometers in this case. All right. So now when I show the surface plot for these, and we're using the same scale, you can see that the reds, they're no longer red, they're orange, meaning a little bit cooler than before. So we have that absorption through the glass there, benefiting that, right? So that's an effect of it. So let's go to the PowerPoint and just learn a little of the things that we learned here. So these ASHRAE comfort parameters that I showed are actually called Fanger indices. We have the predicted mean vote, which, as I showed you here, is from a scale from -3 to 3, +3. And the Goldilocks scale in the middle is where you want to be. And then from this scale, you can get a predicted percentage dissatisfied. I think I said predicted people dissatisfied, but or percentage people dissatisfied. But it basically, that's captured what that was, even if I got the initials wrong. But and then the advanced radiation model is the one on the right-hand side here. So you think of it as a sphere. So it's not just happening at the surface, but in the shaded area where a solid might be, it can also absorb and go through the material as it's passing through. And I'll show you a little bit more about that. So that's with the HVAC add-on. In the standard flow simulation, as I said, you can do radiation, but it only happens at the surface. And that's using the ray tracing method, essentially. So the radiation, advanced radiation that you get with the HVAC can do a bunch of things here. So you can also do, irradiation at the surface, and then absorb it, and then transmit it. And when it gets transmitted through there, because of the change in the speed that light moves through, or radiation specifically moves through solids, it changes that, and you get a reflection, right? And also, this handles not just specular reflection like a ray tracing method, but it can also handle diffuse reflection. And what this is showing you here is just basically how through the thickness of the material, with a higher coefficient, you get more absorption into the solid. And this is showing you, application of a thermal heater. Maybe this is a light with glass on the front of it, and showing you external flow around the outside and the temperature here. And this is showing you as a half symmetry model. So as we were reviewing those setups, I also mentioned that we have glass absorption in the bands. So we can have glass typically lays up into different absorptions based on the spectrum as a banded behavior that we can really capture with this radiation model rather than doing it as a black body, gray body type of situation that you can typically do with ray tracing, setting up the emissivity values. So it's more comprehensive and can allow for, again, real environments that are having these conditions like glass that you need to really include as part of the simulation. And another type of simulation that you might want to investigate is what happens when you're designing an HVAC system. What if a fire breaks out in a laboratory, right? Now, another thing within the HVAC module is the ability to do a tracer study. And then you can track, if it's safe or not, and how much is contamination removal effectiveness. So let's take a look at that with this next example model. So I'm just going to pull that up here. And so the first simulation, real quickly, I'll just load this in, the results. So we can define a heat transfer rate. So this is the location within the lab that the fire, say, is generating a certain amount of heat, and that can be rising up. So the first thing when you're doing a simulation like this is that you run the flow simulation of the HVAC system, okay? So we have an outlet here. I believe this is in the units that we've chosen. It's 211 cubic feet per minute, but I remember that this is 0.1 cubic meters per second in SI, the main SI unit. So that's about 200 CFM. And then it's pulling in air from the outside through these two grates here at the bottom. All right. So with the heat rising through here and the HVAC system fan pulling up the air out through here, we can see the flow trajectory is moving, and as you'd expect, the heat rising up above from where that fire would be. So this is getting the calculation of how the air is moving within the room for that system. And let me just hide that. So now, once that simulation is done, you can introduce a tracer study, all right? And a tracer study is not a typical thing unless you're doing it very frequently that you would add into your tree, right? I think I mentioned this before, is that you can customize your tree and add things that you typically would have within a study. And you can choose that here. And so if that isn't within your toolbar, you can always add that and insert a tracer study through a tool here. Let me see here, results. Usually I just have it in my tree, so I'm not, but there's, here it is, insert a tracer study. So you can insert that into your tree for that particular project as a one-time thing if you wanted to do that. And then we can set up a new tracer study. Let me zoom in here so you can see this a little bit better. And it's similar to the way that we set it up from a whole new project. You can either do it new and set up all the settings manually, or you can go through a wizard. So it's just working on that here. And the two things that we're going to be able to calculate from a tracer study is the local air quality index and the contaminant removal effectiveness. So in our tracer study wizard, we can click through here and we can define different tracers. So these are different contaminants, as you can see. Hydrogen sulfides, carbon monoxide is the one we're going to use, acids and things like that. SOXes and NOXes, I like to call them. Those are all different types of contaminants. And we can add that tracer And then we click on here whether we want this to be time dependent, running it for a certain amount of calculation time with a time step. And then we can find out what's the mass fraction in a location. So we'll put in, say, 80% mass fraction. And then the location can be a volume or a surface, so we'll define that. And then we can define this as a mass fraction mass flow or specific mass flow that's per unit volume, I believe. So mass flow here, we can set up like this. And then you hit the run button. So I'm not going to run this here live, but we already have the tracer study 1 that I've set up, and we'll take a look at the mass fraction of this tracer study. So you can see that the warmer areas here are where you have this contaminant rising up, and it still has quite a bit of mass fraction even at the floor. So if somebody was going to, let me play this, and it'll go back and forth and through the entire room. So we have everything calculated in 3D, and we can show like where the contamination is. So if you were going to try to get down on the floor and crawl out when this fire is, with this HVAC system set up, you probably have more difficulty getting out of there without choking on some smoke and things like that. So you can change the units. Have 2 units that are equally combined to outlet the same amount of flow rate as the original one, but now it's separating them into 2. So that's all done through configurations, right? And then because we're adding 2 different things, and then I add another project where now this outflow here is I doubled. So each unit, instead of having a centralized fan pulling the same flow rate, each one has double. So we can take a look at what this would be. And now we see the colors in black, meaning that the mass fraction is quite low. And you can see that it's not even going up to all the way to 1. And so again, if we play this, you can see that now in this situation with the correctly defined HVAC setup, you are able to get down on the floor and get out of that room safely. So that's what you're looking for. So a couple things, we have local air quality index, which is another way that you can visualize those results. And in the summary, all the way down at the bottom is where you can find the contamination removal effectiveness, which is a value that I had mentioned before that you can calculate through here. All right, so I need, based on time, I wanted to jump to this electronics cooling module so we can take a look at what we can do here with this type of thermal analysis. So why is this important? Because trends in the electronic product design field is increasing complexity in designs, right? Components are evolving, and we can add more complexity because we're using tools like SOLIDWORKS and our ECAD solutions to do these simulations. We have denser packaging, right? Smaller spaces that are driving up the power densities. And we can use, there's aggressive cooling techniques that we can use in smaller enclosures to remove all of that heat that we're generating. Now, I did want to mention that, and I've written a blog post about this in more detail, the differences in thermal analysis capabilities that we have in our Simulation Professional software, which is an FEA solution, versus the CFD that we have with the heat transfer, doing all heat transfer methods. So the main difference is that the FEA, what it's really solving is just basically the thermal conduction problem. The convection and radiation have to be done as models, whereas a flow simulation, as you can see here with the showing the flow streamlines, as it's heating up for a natural convection problem, is that they're heating up and you can see the flow pattern. So it's able to calculate the H value, which is your heat transfer coefficient, which is very localized, and you're going to get different results in those locations where you have air moving and what have you. So there's very localized variations, and that makes it more realistic, right? So I like to use the analogy of a stadium, all right? And so on the left-hand side is where we have SOLIDWORKS Simulation Professional, and on the right-hand side is where we have SOLIDWORKS Flow Simulation, or SWFS. So it's sort of like the FEA approach is like the Goodyear Blimp. It gives you, a good overview of what's happening, maybe a bird's eye view. But if you're looking for more accurate results and want to get closer to the action and more realistic, and you can see what's going on, you want to get in that front row seat by using flow simulation. So you can get very accurate results, even within a small percentage of actual results. And it may happen to just differ by how you set up the problem and how that reflects what is happening in the environment around you. So the third example I'm going to show you is this electronic enclosure. And you can see there's a lot of detail within here. What's not shown in this image is there's 3 fans, and we're going to actually simulate that through a fan curve. So that's why they're just simplified here. And we're going to investigate how we can use a solution to look at 3 different possible ways. So this is a forced convection problem, and we can have a top that has no vents on it, so it's just a solid top. One that has vents on the top, some slots like something's very standard. And you'll notice that there is some venting on the sides here using a hexagon shape as well. And that's true even in the solid top, right? The only thing that's changing is the top. And then we have a custom venting design that's very open, a lot more space is letting the air move out. And that's the idea is, we would think that maybe letting more air escape through the top will be a better solution. So let's take a look at how we can set this up in SOLIDWORKS Flow Simulation. So there's a lot of things going on in this electronics cooling module that really can help you out with solving problems that are just like this. And I'm going to help to highlight what those are. So one of the things is that we have a whole now library of solid materials. All right. So the library has been increased with not only solid materials, and let me see here. So we have additional alloy materials, polymers, interface materials, integrated circuit packages, metal. So that's been increased. Also, I'll mention it here while I'm in this interface, is that we have fan curves, not just the standard fan curves that from PAPs that come with the standard package, but all of these different ones from Comair, Rotron, Delta, all the major fan manufacturers that are used for electronic enclosures that you can list here: Sanyo Denki, Sunon. These are all ones that I have used in different applications, depending on what the customer is using and things like that. And then also we have 2 resistor components. So I'll also mention all these ceramic ball grid array, chip array, small package, and these are all just defined through a junction and junction to case and junction to board temperature. Because again, at the end of the day, what we're looking for is the junction temperature. So the library is a big feature that these are not things that then you have to go out searching for on the internet or from other sources. They're available right from this library that we offer with the electronics cooling add-on. So that's huge. So we've defined all these different materials. For example, a typical chip material for all these integrated circuits on the board. Now, the definition that we're going to define for the flow is just two pressures on either side that are open, in this case, to the hexagon perforated plates on the sides, as you can see here, right? But because we have these hexagon shapes, there's certain geometry, and they could even be smaller. You might see on electronics very small dots and things like that that are used for allow airflow. A better way of approaching that problem is through defining perforated plates. So basically, you can simulate the pressure drop that is happening through a plate like this simply just by defining some parameters in this perforated plate setup. So you can define it as a regular polygon, rectangles, round holes, or even a complex shape. And with this polygon, since we have a hex shape, we have 6 sides, each having a side of about 0.15 inches, 0.14 inches. And then that calculates the free area ratio, which then defines the loss of pressure that is going through that. So that all gets into play into the, let me go back to my slide here. I hit the wrong button to get out of the zoom mode. And so you can simplify the model without having and accurately include these shapes without having to mesh them. So there's a perforated plates, which are again part of the electronics package. And then we have some components that I alluded to in the library where we can define 2 resistor component definitions. So you can specify where the hot side is, okay? So that's the outside ambient selection. The components that are included within here, so we have the board to junction, and then junction to case. And those are then defined with the amount of heat that is being dissipated. And then the ceramic ball grid array, 10 by 10 millimeters, has in this case, the first one, that thermal resistance value in the units of Kelvin per watt. So every watt, this is the amount of temperature that it is increasing. So again, you're simplifying this package here, and you could have several of these, and these are all defined all the same way, just by a simple vertical circuit, thermal circuit. If you think of it like as an electrical resistor, this is the thermal resistance, and you have 3 nodes: the board, junction, and the case. And when you define this thusly, you also have a goal that you can set up automatically to give you the junction temperature, and then set that up as a goal that you can use for convergence if you wanted to. So that's nice to have. And then we have printed circuit boards. And you can see here that we have a simplified solid model that is defining the circuit board, but in reality, there's different layers of copper on that and everything, and we want to capture that. So we can define a printed circuit board in a way that, again, through the library, you can set this up. And what it does basically is you define, these are automatically set up. So you have FR4 material, which is your dielectric. These are all the material properties for that. The conductor, these are all the properties from copper. You put in your total thickness of the PCB, And then all these values, which are in plane and then through thickness, conductivity, all of these ones in gray are actually calculated, right? And then for doing a transient analysis, you need the effective density and effective specific heat. But you're basically setting up in a table that you can get from a PCB manufacturer, the thickness of each layer and the percentage of copper of the conducting material is on each one of those layers. So this is a simple 4-layer board and defining the amount of coverage of the conducting layers on that. And what that then does is, as I mentioned, heat can spread out along the board laterally, but through the thickness, it's not going to conduct temperatures through it. And that's how it is in reality when you have PCBs. All right, so we have these solid lids, and then we have different configurations that are set up here. Solid lid, the custom slotted lid, and then the standard slotted lid, right? And I showed you last time how you can clone a study, right? And copy the results, and then just this would be a slotted study. And then using configuration, we can select the slotted lid configurations and then just clone those 2 studies and then run those in a batch run. All right. And let me load these results for the solid lid. And once all of that is done, you have all the results for all 3 different situations that you want to set up. And let's take a look at some of the results. So we have the no vent trajectories shown here. So there's an animation that you can show. And then we have one with the standard slots. You can see the fans that are pulling in, the air patterns are different. And then you have solid results, no vents at the top. We have the custom one with the custom vent design. And then this is what you can do. You can compare the results. So I wanted to show you how you can do this through here. So the compare results. So we can take a look at different things. We can take a look at images. We can take a look at any one of the plots that you want to compare, and everything will be set to a standard slides. But we're going to do this just as charts. So we set up some goals that we want to use for comparison. And then we choose which projects that we want to compare, right? And you can see here then the results after you hit the compare tool, and you can show these as a table, you can show them as a chart, and I prefer to show this as a bar chart. And then you can export that out to an Excel spreadsheet, and it dumps it out directly into a format just like this. Then you can present these results, putting them into a PowerPoint, just like I had done here. So it's a great way of comparing different designs and getting to the best solution, which happens to be the lowest one is the one with the solid, the one in the middle. And the reason for that is that in a forced convection problem, as opposed to a free convection problem, the fans are doing the work of pulling the air through here. So let's take a look at some of the plots. Let's show the temperatures on the board, on the display board in the back there, on that board at the bottom. And once that is done painting it, I'll also show you the ability to probe the results so you can get a finer result of what the things are shown on the screen. right? So you can probe things at these locations wherever you want, drop those, and it helps you, even just hovering over them, you can utilize them for reading the results. It can help you to interpret this. So even if you change to a different values like heat transfer coefficient, those values will stay on there, and then you can use that to compare. And even you have the ability to change these flags to show multiple things, not just a single thing. When you click on a probe, it shows you what is shown on the screen, the color based on the legend, but then you can add additional parameters on there as well. Another thing that I didn't have time to go into today to show you, but when you're setting up your ECAD solution, right, if somebody has defined within the properties of each of the components, you can specify the material property, the amount of heat that is being given off, and then that can be utilized, imported directly into flow simulation. So very quickly, you can define all of these heat sources just by importing those into here. So for example, you can see the material properties is being imported as well as the volume heat source. So that's through an option of just importing the data from the model. It can save time dramatically. So a few of the other things that I showed you here is 2 resistor components. So these are all the different types of components that are in the JDEC standard models that we have for a vertical solution. Like I mentioned, board to junction to chip or to case. I showed you the perforated plates and the ability to define those in different ways. I also talked about real quickly about fan curves and the ability to even define your own fan curves if you don't have those, or choose them from the library of the popular fans that are available from Delta, Sunon, Sanyo Denki, and many others. And then I talked about the printed circuit board to be able to define that. You can't do it otherwise in any other add-on package for flow simulation. Now, just real briefly, I was maybe gonna, I knew I was probably gonna run out of time to show you this lighting model, but I wanted to just briefly mention that there's an application, if you're in the lighting industry, LED lighting industry more specifically, and you have these diodes. So the diodes can be modeled as a 2 resistor component, and then you might have glass that is covering the front of this light fixture, right? So that's an application that can use both of these add-ons, HVAC and electronics cooling, the LED lighting industry. So if you're in that, you maybe want to investigate that a little bit more. And just if you're interested, this is a natural convection problem. So the heat is just rising due to the heat coming up through these vents around the outside and then coming out here. So another thing that you can calculate is for UL requirements is the temperature on the outside of the bulb. All right, and this is a standard test that they do in the lighting industry where you enclose it in a box of a certain size and you run it like that. So we're getting towards the end of this, and of this webinar. I just wanted to mention other applications if you're interested in doing external aerodynamics, internal flow for large buildings or 2D transient simulations. We have those capabilities, as well as doing pressure drops, pressure on dishes, data centers, valves. This one on the bottom right is a drill bit head. So we can do that for oil and gas industry is where this one comes from. Valves, rotating flow, transient flow of a medical dispenser. So flow simulation has a lot of different things, and you can read a little bit more about why you might want to choose flow simulation as a solution There's a data sheet, and all of that can be done. If you haven't done it yet, click on the open up the Handouts section of your GoToMeeting, GoToWebinar interface, and you can click on each one of those and download them right now if you haven't done that already. So if you want to find out more, you can go to our website. I listed that here. And I'm going to hand this back to Joelle, and while she's doing that, I'm going to look at what questions we have.
So lots of information, different applications. I'm assuming if you're on the call, either it was for general information or one of those, or both together apply to what you're doing in your day-to-day life, at work, or in your own business, whichever it is. We want to make sure that we continue this conversation with you. If you do have an application where this fits and you see a fit for this and a need for this to improve what you're doing today, you can either reach out to us directly. You can share this video with others. Of course, it's been recorded, so you can access it just by clicking on the link that you got to get onto it. You can do it that way. It will ask if it's a new person to register, but we'll take them directly to the recording. So as easy as that. Or you can go to our repertoire of all of our webinar recordings and see them that way done for Eastern Canada, but of course accessible by anyone who's on this call today. You're all welcome to join. Your resellers are, of course, another great source of information and can take the time to tailor this to your conversation, to your needs, which would be the next step for anyone looking at more details in this. Were there any questions, Joe?
Yeah, we have a question here from Victor. Just real quickly and brief, he's asking, I was showing the radiation source from the sun, and he's asking whether we can define other additional radiation sources. And yes, you can. You can define radiation sources from an object anywhere within the domain. So it doesn't have to be environmentally. As I mentioned, we have solar radiation as well as body-to-body radiation. So you can define radiation sources from wherever as well.
Wonderful. All right. Well, we give you guys back 2 minutes of your time from the hour that we have reserved. Joe, thank you so much for taking the time going through this information with us, and hope to see you all on one of our other future webinars in the remainder of the year. Have a great day, everyone. Bye for now.
Thank you.